our next speaker is Quentin Ocem, a business development lead from Adacor. He will discuss self-verified software. Quentin, you are welcome to start now.
Thank you. I'm assuming you're seeing my slides now, you're seeing my screen?
Yes, we do.
Okay. All right, so my name is Quentin Ocem. I work for Adacor, which is a company that is specialized in the development of development workshops and tools for safe and secure software development. And I think it's an interesting segue or follow-up from the previous presentation, which was focused on what you do to increase the safety of the feature capability set of the machine learning algorithm. I'm going to talk about the other piece, the piece that you still have to write by hand, may that be firmware, driver, communication layers, safety modes, and so on and so forth. And in particular, I'm going to introduce this concept of how do you verify that software, and is there a way to somehow make that software verified itself, or make the verification of that software to some extent embedded in the software itself. Let me just get my focus back. Okay, now. And I want to start by perhaps addressing a misconception that I've encountered a lot on the field. There is this idea which is driven by common wisdom. It's also driven by safety standards. And this idea says that implementation and verification should be two independent activities, because of course, if you are the developer of a piece of code, you're not the best one to verify whether or not this piece of code behaves as intended. You have a bias towards believing that your work is correct. That is true to an extent, but if you take that to the letter, you will reach a situation where the developer himself doesn't care too much about verification anymore, which ends up making that much more difficult. I've seen cases to the extreme where software that is being delivered to the testing teams becomes completely untestable. And at the very least, if you take this state of mind, verification will happen later in the process, and problems that could have been identified earlier and thus cost less to fix will not and will be found at integration testing or later, and perhaps be causes of cost increase. So of course, at some point, you need somebody to verify the software independently, but the developer is the first line of defense, and it's important to give him tools to be able to run and define as much as possible the verification of his software. Now, why do we need to express software verification? If you look at the overall software development cycle, and I'm talking about really activities that pertain coding, I would say, you need a mean to specify what is the software supposed to be doing, the intent of that software. Those could be a requirement coming from your high-level analysis, but those could be constraints or various properties. For example, thou shalt not have a buffer overflow in your code is not really a requirement in the functional sense of the term, but that's definitely a property that you would like your software to have. Then, of course, you need a mean to implement. That's the typical programming language that you might have. And then from those two items, you need a mean to verify that the specification that you expressed earlier is indeed what has been implemented by software. This is traditionally done by things such as review, testing, and static analysis. Now, what we're going to talk about here is a programming language that allows to define together the actual implementation and that specification associated with tools that are going to allow to verify dynamically and statically the properties and requirements that and the specification that is described before. And to illustrate this, I'd like to start from C. This is a typical code of a piece of C code. It's actually a nice one because in that specific case, the developer decided to name the type of the pointer parameter of this update function. Of course, in the real world, we would have a lot of comments around that describing what is the intent and the constraints surrounding that piece of code. But what I want to illustrate here is what does the language give you? What can be automated in terms of analysis? And truth being told, we don't know much. We know we have a float. We know that we pass it as a pointer. We don't know if it's an array. We don't know if the pointer can be null. We don't really know if the value is going to be modified, and so on and so forth. And I want to contrast that with the same level of specification of the language that I'm now going to introduce, which is called Ada. This is the exact same level of specification. I'm not even adding additional capabilities that the language allows to add in terms of functional requirements. And here already, there is a lot more that I can express on that very simple piece of specification. I can say this floating point temperature has to have 17 digits of precision. These are decimal digits, which means to the compiler, please verify that you can implement that on 64-bit, and please do so if you can. Otherwise, refuse to compile. I can provide a range of value. Here, I'm working in Celsius degrees. So from the absolute 0 to, let's say, 1000. That gives me two things. First of all, can I represent those values in the type I'm describing? For floating point values, more often than not, that would be the case. And second of all, every time I'm using an object that is a temperature, am I within the range of acceptable values? And this enables a lot of verification, both from the static and the dynamic side of things. On the actual procedure, we call that a subprogram in Ada. We can define the way that that parameter is supposed to be used, the intention. So you see here, I don't have a pointer. What I have is that temperature is a value. Now I know it's a single value, which is in mode in-out, which means that I have a value as input, and that value can be modified by the procedure. So now we can start to see at the very low level with very simple things, how useful it could be to have the ability to specify at the language level, the intention and the constraints of some of the entities. So this is how you express. How do you verify? So let's take this example. I'm reusing that temperature type. I'm declaring here a variable named x, which is of this type, and I'm assigning to that variable the result of a multiplication y times z. How do I ensure that the multiplication is within the range that I expressed before? Traditionally, again, there are two ways. I could do testing and test various values and make sure that I don't have an error here. Ada will actually insert a dynamic verification if I ask it to. I could do that by static analysis. Perhaps that corresponds to a code patterns that is a known bug. But really, what I will want to do here is to use something that is called formal proof that I'll describe a bit later, which is going to be a way to guarantee mathematically that this assignment is always correct, no matter how the code is being called. So, and that's really important to understand the difference between that and static analysis. Static analysis will look at potential bugs from patterns. Formal proof will demonstrate correctness no matter what. And there are a lot of things to demonstrate if you look at the code. I mean, this was just a single example. On that other example, I have a lot more questions to ask from a safety point of view. In this case, I'm indexing an array. So am I in the bound of the array, or am I doing a buffer overflow? I have some arithmetics that could be out of the range of the expected value, but that could also overflow the machine values. That means, to have value to positive going all of a sudden negative. So another overflow, I could have a division by 0. And of course, all of these things could be uninitialized. So that's a lot of elements to worry about on a single line of code. Having something like static analysis or testing will allow you to gain some confidence that most of these are okay. The key is being most of these. From a safety point of view, sometimes you might be able to convince yourself that the odds of having failures is low enough. It's not always easy. But nowadays on automotive systems, you also have to worry about security. You don't want to have few defects. In particular, when you look at things such as buffer overflow, you want to have zero defect. And that's really where having formal proof embedded in the software itself will help, because it will allow you to reach that level. Actually, from a software developer perspective, it happens to be quite easy to reach this kind of absence of buffer overflow demonstration. This is really the baseline on which you can start to build more complex and more advanced verification. So far, I really just described the inherent constraints that you can have on the software, but you can go a lot further than that. Let's carry on talking about low-level memory management, device driver, and so on and so forth. And let's assume that I have memory that I need to manage. And on this memory that I'm managing, there is a secure buffer that has some magic hardware protection against adverse reading. And this buffer, I need to be able to move it in the memory. For example, I need to be able to extend it, shrink it, and so on and so forth. And I want to make sure that when I move this secure buffer, all the data that was before in the buffer is erased so that there's no leak of data. But I don't want to erase more than what I need. Otherwise, I'm spending cycles doing essentially useless operations. So this looks like something like this. I've got this buffer in green. I have a from region, which is here in blue. I have a to region, which is in orange. I'm moving my buffer from to to, and you see in pink is the region that is common to the two locations. So if I move from to, what I want to erase is the blue section, and I want to ensure that I'm erasing all of this section and only this section. That happens to be something that you can formalize in the software itself using Ada. And actually, what I'm using here is an extension of the Ada language, if you will, which is called Spark, which is allowing to do this formal methods and formal verification. So here, using the very language I'm using for developing software, I'm not learning a new language. I'm not writing something in a separate file. It's in the very language at the very point of the specification of that subprogram, which is performing moving that memory region. I'm stating that as a post condition, that is to say, after the call of that function, something has to be true. For all the bytes that are in my memory, either the byte is in the from region and not in the to region. In such case, it has to be erased. Otherwise, it shall not be erased. Two interesting things here. First of all, this is code that is quite readable for a software developer, right? And as a software engineer, I can write that, I can understand what that is. I could even, in some respect, execute it. That very specific piece of code, however, is expressing a requirement on the entire memory. So as a matter of fact, running this every time I'm doing a move is going to be very slow. I might want to be able to test that on a few specific cases, just to get confidence on the fact that this post condition works. I can even debug it if I want. But the real power here is that I have been able to express a requirement on the entire memory, and I can verify formally, mathematically, that the implementation of that procedure, which looks nothing like that, right? It's probably a lot of optimization for a lot of special cases, is strictly adhering and respecting that post condition. And as it turned out, this is not a theoretical example at all. That's actually an extract of a real life case example that we've seen with one of our customers. So why is all that useful? Why is all of that different from other methodologies? The idea really here is that you have software bearing its own verification mixed with the implementation. So essentially, in the same program, you have both verification and implementation. And the tools can untangle those two things. When you compile for production, of course, you're going to strip all the verification element at compile time. So you will have code that is binary efficient, similar to C. In terms of executable semantics, it's the same model. It's actually using the same backend. Our toolchain is GCC based, and we're just completing the LLVM based one. But because it's in the same place, you have, I would say, intimacy between those two phases. You have by construction traceability, which means that it's at the same place, so you can tell which verification corresponds to which construction. You have consistency with implementation. You have the fact that the verification that is being expressed in the software is referring to the very entities that are declared in this software. So as a consequence, you know that it refers to the right thing, right? You're not in a situation where you might have a Word document that refers to items that actually are misspelled or may not exist anymore in this form in the code. Which leads me to the next point, which is maintenance. As the code evolves, you're going to very organically make its verification evolve at the same pace and at the same in the same place. And last but not least, in terms of cost savings, the verification is performed as the code is developed. The tools that you're using for formal verification, formal proof, is run by the developer on the developer desk, which means that the odds of introducing an error that we pass to the next team is reduced. And of course, there are things that you will still have to verify later down. But at least for everything that pertains to this software, you have reduced massively the risk of having errors to have to be discovered by either a unit testing team, an integration testing team, which, as we all know, the later you wait, the more expensive it will be to get fixed. That cost I want to stress because that is actually measurable. A few years ago, we asked VDC research, that was back in 2018, to measure the differences between Ada usage and other languages, in particular C. So that graph that you see here is their findings, so for their own market study. And they looked at people that have used Ada for a long time, what are their costs for the development process. That includes development and verification compared to other languages. You have the reference here. What's interesting is that what they found is that people that are using Ada on average are claiming up to or down to 38% savings compared to the C language. So that's essentially the message and the talk I wanted to share with you today to demonstrate the possibility of using a different formalism than the C language to mix two aspects of the software verification, the software development process, and result in this very effective environment that's going to improve how your team are developing the software that they still have to develop by hand.
Yes, thank you very much, Quentin, for this comprehensive presentation. We do not have questions right now. Maybe you would like to use the time you have, to share some thoughts with us or to discuss key takeaways from your presentation.
Absolutely. And one of the things that I could share with you guys is a couple of references, actually. So the technology of this talked about today is coming from historically the aerospace and defense domain. So it's been used for over 35 years now, 40 years now, in avionics, space, commercial avionics, defense, and so on and so forth. But the reason why we're talking about it here is because we've seen an increasing interest of formal methods and Ada and Spark in the automotive domain. Just as an example, just as it turns out, you will find, if you Google it, a blog post from QNX on their experience around Spark and Ada, so the technology I've presented today, and how they come to from a very skeptical place, where they essentially said, we develop code in C and we just put tools around it and processes around it to improve safety and security, to a place where they're like, oh, wait a minute, there is something interesting to dig here with Ada. Yeah, that's a language that is worthwhile considering. We have a couple of other references here, none the least being NVIDIA, which made some similar announcements a couple of years ago. They actually have a 45-minute webinar where they explain why they selected that technology. So there's definitely a trend that we want to talk about and share on people that are looking for formalisms outside of the C language to improve those processes. And this is a very serious alternative that has been used now by a number of actors that is definitely worthwhile checking out. That's our job, to accompany people to investigate those things, to prototype those things if they are interested.
Okay, great. Thank you very much, Quentin. Dear audience, please feel free to visit virtual booth of our partner, AdaCore. And get in contact with the team, and we will continue.